Hello everyone, and welcome to the vacuum transport seminar. We first do the quick introduction. On the next slides, you can see a short overview from today. We're very happy to welcome today's lecturers or presenters. The first one is Burak Alpkaya. He's a master student at ETH Zurich, and his talk will be about analysis and simulation of a control strategy for levitating linear induction motors. And after his presentation, we go to the Slido page, and you can already log in to Slido and post all your questions during his presentation. And afterwards, we have a discussion on them. And then the second talk is by Miguel Molinari from Molinari Rail. He's an industry expert, and he works with the Swiss Loop team. And after his presentation, again, the same procedure with the questions on Slido. Then on the next slide, you can see how Slido works. So it's a simple interaction tool. You can ask your questions, and you can also upvote other questions from other people. So just go to your browser or take your cell phone and go to slido.com. And there you can enter the event code, which is Back Transport Seminar. Exactly. I can put it in the chat. Okay, so that's it from our side, and I would like to hand over to Burak, and yeah, thank him for his talk.
All right, thank you, Natalie, for the introduction. So today, I would first like to thank you for your interest in the presentation and in the seminar. And I would like to start talking about linear induction motors in general and explain briefly how we can get some propulsion and levitation forces from our linear induction motors. I will not dive into the physics, but just give a high-level overview of what we can hope to achieve. I will also touch briefly on some of the design limitations that we face, and then go over to our system models with which we can try to define our signal variables and different controllables. And lastly, I will go over to the main topic of interest and try to explain how we want to achieve our control objectives with a given control architecture. So firstly, you can see on the bottom here, I hope it's legible and visible, a linear induction motor drawing. Usually the primary, it's this one here, is made of an iron core, and it has many teeth around which these coils are wound. And these are arranged in such a way that if we apply a three-phase AC current, which is usually the case, that they produce a moving magnetic field across the primary, which can then induce some eddy currents in the secondary. And then, of course, we know that currents in B fields are subject to Lorentz forces. And without going into the details, this is how we basically can hope to achieve some propulsion forces in the X direction and some levitation forces in the Z direction. Of course, also there's this amazing YouTube video from the father of maglev, which I would recommend to anyone who has 20 minutes, and I would really recommend it. Right. So this is a animation from a simulation that Matthias Stressler made last year. He designed the linear induction motor of the pod for the Swiss Loop team last year. And in this simulation, you see actually a double-sided limb topology where a primary is on one side of the secondary, and then on the other side of the secondary, there's another primary. In our case, we want to generate some levitation forces, and due to the nature of the linear induction motor with a double-sided limb, it's not really possible to generate levitation forces. So in our case, you can just imagine that we will only have the top primary and the secondary. But here you can basically see the magnetic field as it moves across the primary, and you can also see the movement of the secondary with respect to the primary which will be actually the speed of our pod. Of course, in our case, the secondary is fixed and the primary is moving, but this is just simulations, technical stuff, so it's not really a difference. So we want our linear induction motor to get us from point A to point B, and this means that we need some propulsion forces. The propulsion force needed for this is dependent on actually many different factors. So we have seen that the magnetic field moves at a certain speed. This is called the synchronous speed, and is calculated by this formula where tau p is a motor-related constant, and Fp is the frequency of the current that we use to supply the voltage for the primary windings. And the slip is a characteristic of asynchronous machines in general. Asynchronous means that the speed of the actual machine will be different than the speed of the magnetic field that's moving. And we can try to imagine what happens when the magnetic field moves as fast as the actual linear induction motor. In this case, the magnetic field with respect to the secondary won't be moving at all, which will mean that we won't be able to generate any forces. On the right-hand side, you can see also some plots from Matthias's semester thesis last semester, and he derived the dependence of the propulsion force with respect to different parameters. For example, you can see if we increase the frequency, then we, of course, increase our synchronous speed. And this also means that we increase the speed that we can achieve before we reach zero slip. So in a way, the maximum velocity that we can hope to achieve is limited by the frequency that we use to supply our current primary windings with. Also, we can see that adding more pole pairs, which is to mean adding length to the linear induction motor, can linearly increase our generated thrusts, while increasing our current quadratically increases the forces that we can generate. Of course, this doesn't mean that we can just infinitely increase any of these quantities. Unfortunately, we are limited by many different factors, but it's just nice to know that we are trying to maximize all of these and then looking at the forces that we can generate with the maximum values. Also, because the topic of today is a levitating linear induction motor, we want to actually be flying on our way from point A to point B. And this means that we have to generate some levitation thrusts that can overcome the gravitational force that's pulling the linear induction motor downwards. In many cases, the mathematical models that are used for modeling the linear induction motors are subject to many simplifications, and they cannot really encapsulate all of the different effects that can happen. So we make use of finite element analysis methods such as ANSYS-Maxwell simulations, such as the animation that we saw previously, to actually be sure that we can generate the forces that we want. And this is a simulation done by Rahel, who is designing the linear induction motor for this year. And you can see here on the x-axis the frequency that is varied, and on the y-axis the thrusts that are generated. There's two sets of lines, one at 0 meters per second pod speed and one at 14 meters per second pod speed. This is the first target that we hope to achieve this year. So we simulated the actual thrust that we generate at each frequency at these two different speeds. And then we saw that basically if we can supply the windings with 200 hertz of nice sine waves, then we can achieve a 1.5 kilonewton levitation thrust, which means that as long as our pod is lighter than 150 kilos, that we can actually have it be in the air. Also, we are also, of course, subject to some design constraints. On the right, you can see this I-beam. This specification was given by Hyperloop for their own test track, and all of the university teams that wanted to go to their competition, of course, built their own test tracks according to these specifications. But this is not to say that it is the best possible solution. If we look at what we can change and what design freedoms we have, we can either change the linear induction motor topology, or we can try to change the track topology. And we can just, for example, if we can change the tracks, we can think of adding another track just to make stabilization easier. Or we can try to add some iron backplates that are used in many research papers to guide the fields in a more efficient manner. Also, if we cannot change the track, we can still try to come up with some ideas. For example, double-toothed limb, as shown here, could maybe be used to guide the magnetic fields more towards the left or the right sides of the limb to hope to achieve some control in the y deviations or the angles. Another option could be placing a single-sided limb on top of a double-sided limb to achieve a triple-sided limb, which can also stabilize itself while levitating if it can generate enough levitation. I will try to also, in the course of my semester thesis, try to simulate and come up with some control schemes for such topologies. But for now, we are working with the usual single-sided linear induction motor. And in this case, we can try to define our system models. And at first, it makes sense to look at how we define things. So this is our pod, and the linear induction motor is embedded in the pod. It's floating right now with an air gap between the I-beam and the pod, and on top of the I-beam, of course. And this is how I define the coordinate system in this case. And we want to, of course, reach a certain velocity, and we want to not go over the track, so we want to keep within the track bounds. In the y direction, we do not want any deviation, since it's not helpful at all. And we don't want any velocity either. And finally, in the z direction, we want to keep to our air gap with which we calculate the generated forces. Of course, as the air gap decreases, the forces increase, but it's there has to be some mechanical clearance as well. On the right-hand side, I also defined some angles. The yaw angle is when you're looking at the assembly from the top, and the pod is kind of skewed towards the left or the right. The pitch angle is when you're looking at the system from the side, and the pod is on an incline. And the roll angle is when you're looking at it from the front, and the pod is kind of tilted in this way. Of course, we want all of these angles to be 0. So this is our control objective for our angles. I said with the usual single-sided linear induction motor, we can try to control most of these things, but we may also come up, face some limitations. So the velocity and the position in the x direction are controlled then directly through the sum of the propulsion forces that we generate, and the actual levitation force is the sum of the levitation forces that we can generate, and this can regulate our z position. Also, we can try to regulate our levitation forces to be different in different parts of the linear induction motor, and this can give us some kind of control over our pitch angle as well. As said, with the usual single-sided linear induction motor, we cannot really try to control our y deviation, our yaw angle, or our roll angle. So these have to be, for now at least, purely mechanically restrained. Such a simple drawing of a mechanical restriction could maybe give you the idea. So coming up with a mechanical system model, here illustrated for 5 pole pairs, we can see how the forces act on the centers of the pole pairs, and then we can try to use this model to come up with the actual angular accelerations as derived from the torques and the sum of the forces that we are encountering. An electrical, very simplified model could be like this, where we have a three-phase current that's phase shifted by 120 degrees each. And we have to supply our pole pair with this current, and it's in a star circuit. So generally, when we have some kind of slow mechanical dynamics, as we have seen, and some fast electrical or electromagnetic dynamics, many control systems make use of what's called cascaded control, where the outer loop is used for slower dynamics and the inner loop is used for faster dynamics. And as long as the inner loop can be thought of as being 10 or 5 times faster than the outer loop, this means that the inner variables can be seen as perfectly controlled by the outer loop. So each controller only has to care about their own references. Also, as an implementation problem, we want, as I said, nice sine waves, but we cannot really put an we cannot connect our linear induction motor to the normal wall plugs. So we will have to kind of find a way of generating our sine waves from a boring DC battery voltage. And what's commonly used for this case is just to have a three-phase inverter in such a configuration where each of the switches can be drawn with pulse width modulation signals to actually achieve fine-grained control so that we can generate such nice waves. I also wanted to just show you how we can try to transfer our mathematical models to some simulation software where we can play around with some different ideas and then come up with what architecture works best or what kind of values we should use for our controller gains and stuff like this. So we are using Simulink, which is pretty much the industry standard for control applications. And I would also like to kind of mention some of the different ideas of control schemes. It is quite early in the process, and the actual control schemes are yet to be developed, simulated, and implemented in software. But there seems like to be 3 main areas of achievable control schemes, and one of which would be scalar VF control, which is where it can be done in open loop by calculating beforehand what voltage and frequency it is needed for each of the possible references. In our case, we could use our simulations to actually find some values that are needed here, or we can try to use some more, not really advanced, but more complicated methods to transform our voltages to actually apply some advanced control algorithms, such as field-oriented control or directness control. And in the end, what will probably be implemented is a mixture of advanced mathematical estimators that are needed for the more advanced methods, and also our simulation results as in the form of lookup tables. So an example of a lookup table that could be used for scalar control in the first phases of the implementation could look like this. This is basically an extended version of the plot we have seen before, with more fine-grained velocity values at 2 meters per second each. And we could, for example, try to estimate at each velocity level we have what optimal frequency we should be using for our windings, and then a feedback loop could be used to actually make sure that those windings are driven with the exact given currents. I think that's all from my side for today. I hope it wasn't too boring, too simple, or too advanced. I'd like to thank you again for listening, and I'm ready for your questions.
Thank you very much, Burak. It was very interesting. So now we would like to switch over to the questions. So to the audience, please feel free to type in your questions if you haven't done so already. for a short discussion round for roughly 5 minutes. So there's one question. Somebody wants to know, why do you still use the I-beam from the SpaceX specs?
Of course. So this is mainly, oh, I guess you could also answer that, because this year we hope to attend the European Hyperloop Week. And also in the next years, if the Hyperloop competition comes back, then we are quite certain, I guess, that the previous test track specifications will be kept. I mean, we are probably only designing for testable systems, and unless we want to build some new test tracks, then it makes more sense to build for what we do have.
Yes. Okay. Thank you. Then the next question, what is the biggest stabilization challenge when it comes to levitation?
I think I can maybe go back here to this slide. Well, the actual challenge, if we were to do it in a controlled manner, would be to try to control the Y deviation, because there's not a lot of playroom in there, and it's by itself unstable, because if the limb is kind of like, if it has a positive roll angle, for example, then the fields will actually repel each other away from the I-beam, so the limb will want to fall over. So if we could find a way to control it, this would be the hardest one. And in this case, probably the hardest thing is if we are still using the mechanical restrictions and our usual single-sided limb with divided pole pairs, the pitch angle could be quite challenging, because it really depends on setting the center of gravity of the whole pod really accurately and knowing that. Also, as you have seen from the first, from this slide, the propulsion force and the levitation force are actually kind of coupled at each frequency value. And you also see that the maximum of the propulsion force and the maximum of the levitation force don't really like to be at the same place. So that's also a challenge.
Okay, then the next question is, could you think of a better structure replacing the I-beam? What would be best for a linear induction motor?
Honestly, I do not really, I did not investigate linear induction motor theory too deeply, but in the literature you can see a lot of systems where iron is used so that attraction forces can also be used for the levitation instead of the repulsion forces that we are thinking of using. So that means they kind of hang the linear induction motor on the I-beam instead of making the linear induction motor repel itself from the I-beam. That could be a VERTI notification. And also in general, just using two tracks, such as in trains, would also make things a lot easier, I think. But yeah, sorry, I don't really have an accurate answer for that.
Okay, and then we have time for one more question. The question is, at which rates do you have to run your control loops to be safe? Could you elaborate?
Sure. The actual linkages of the electrical system are honestly not yet integrated into the models, but as it looks, I cannot really tell you how fast we have to go, but I can maybe tell you that the outer loop is probably going to be run at 200 to 1 kilohertz, while the inner loop will be run at whatever the maximum current sensing capabilities we will have. So in our case, I think we have enough calculation power that we don't really need to worry about where the lowest bounds are, but they will also be very interesting for my semester thesis, and they will be included in the final results for sure. So you can maybe try to check that out once it's published.
Okay, thank you very much. And again, thank you very much for your input talk and your presentation. Thank you very much for the contribution to the seminar. And yes, now we'd like to go over to the next presentation by Miguel Molinari. I quickly make him also a co-host so that he can share his presentation.
I'll stop sharing.
Hello, Michele. Welcome to the seminar.
Hello, do
hello.
you hear me?
Yes, we hear you.
Perfect. I still try to show you my screen. Do you see my screen? I don't think so.
We do.
Ah, you do?
Yes.
Okay, very well. Thank you very much for this invitation to participate at today's seminar. I just made it on time. I'm very happy. And traffic was too brutal. I'm Michele Molinari. I'm the founder and president of Molinari Rail. And we are a sponsor of Swissloop since quite a few years. And we are a very proud sponsor, and we value and like very much what you have done so far in the last years. And just a short introduction to what we do. We are a Swiss mobility technology group. Our headquarters is in Winterthur, and we have offices in Vienna, in Schwaz, in Austria, as well as a factory in Germany. Out of these locations came also the contribution to the latest part of Swissloop. We work in system engineering for passenger and for freight vehicles. We manufacture components, and we collaborate with other partners in the implementation of transportation systems worldwide. We are about 250 engineers and specialists, and we work since quite a few years around a few key topics. One of them is, for example, propulsion systems, where we work with customers and partners on the implementation of hydrogen fueled passenger trains. We work on new solutions for the emission reduction in public transport and in maintenance vehicles. And we work also very much on the passenger experience in metros, etc. And the overall goal is to take new technologies and bring them and adapt them for the use in public transportation, in railway systems, but also in other systems like buses, monorails, and hopefully also Hyperloop. This gives me a good transition to our key topic of what of course interests you today. And if I go back, and when I started to see Swissloop a few years back, I laughed because already on 1993, in the company where I worked in Zurich in Electrowat, colleagues of mine were working at the Swiss Metro. I don't know if some of you guys have studied Swiss Metro, which today the idea came back to a certain extent. in the cargo souterrain. And so I'm very happy that the good ideas have not been completely buried. But if we look back, already at that time, I was exposed the first time to this idea of transportation of passengers in a tube in a new way with magnetic levitation and with high speed. Since 2019 and also 2020, we have ongoing discussions with Hyperloop transportation technologies through personal connection with some of the founders. And you see here some pictures when we visited Hyperloop transportation technologies in Toulouse. You see there the 300-meter test track where they test the vacuum and the evacuation of the air. You see there also how big the tube is. And there they have the first capsule, we would say. And right now we are collaborating with them with regard to bogies and other aspects of the capsule and the implementation of the system. From my point of view as a professional in the transportation industry, I focus, of course, not only on the technology, but also on how do we implement it and how do we make it a viable business case. We, of course, value very much what you do at the ETH and in other universities for the development of the core technology to get more knowledge, more insight of how the systems work. We look more at the integration of all this to make it happen at the very end. So if we, for example, design the capsule or we get the capsule, we discuss actually things like how we integrate the propulsion into a bogie or whatever can be called, where the whole traction force is being applied and the capsule rests on top of it, but also how the capsule itself is designed, because we want to transport passenger in it in a safe and comfortable way from A to B. And at the same time, it has to be in a way that it is acceptable for the public to do it. We have seen that there are quite some environmental issues also inside the capsule to take care of. So the whole integration of the passenger compartment, the doors, also the interface from the door to the tube, the environmental system itself, because we look at the capsule like a self-sustained item. So this is doable. The key elements are there, but it is one of the next steps to be done. One of the very important things is where we look at is the whole dependability of the systems and the reliability for the operation, and of course for a reasonable maintenance later on in operation. This whole reliability and availability of the systems in the capsule, in the tube, are key factors for the safety of the whole system. Without that, it will be very difficult to achieve certification. This certification is key to later be able to transport passengers. Imagine if you take a train today, that the train can go on the rails and transport passengers, etc. It needs a certification, a very thorough certification, which takes a long, long time and employs a lot of people. and costs an awful lot of money. And this can only be done if all the systems really work and there is a clear process to be followed. For the Hyperloop application, Hyperloop TT, HTT, and TÜV Süd have worked over the last few years and developed a key, let's say, a key document where the most important aspects, which then later on lead or will lead to the certification by the authorities of such a system. Just that you imagine yourself a little bit, a Hyperloop system has to follow quite a lot of norms and regulations. And I personally think that it is about 60% kind of a railway system or similar to a railway system, maybe 20 or more percent like an airplane. And maybe the rest will be 10% norms and regulations out of other means of transportation or industries. So this has to be packed together, and this is a very important task for later being able to put into operation and to transport people in such a system. So we do that also in our railway project. Certification starts the very first day when a new project starts in engineering and design. And when we look already forward at the end of the project where certification has to be achieved. Other issues we look at or aspects we look at it right now are, for example, construction methods of the tube. And the land use, how much land is necessary? How do we build it? Do we build it on top of other existing infrastructure, etc.? And how is the station design being done? This is a special issue, in my opinion, because we have to see that in a station, the people have to board and deboard. So we have a docking system between the outside through the tube into the capsule. Then we have to undock and then somehow inject, I call it injection or extraction, the capsule into the tube. And this is quite an interesting aspect of it, and it's not only the technology side, the design side, but also how do we operate it safely, and what are the protocols behind. So there is still a lot of work to do, and there are many, many aspects to be taken into consideration. At the same time, we work also on the business side of it. What is the business model for the implementation of such a thing? For example, track lengths, how many people are being transported, what kind of velocity or speed will be done. Because this goes straight into the business case and the business plan, and brings us back to how do we finance such a project. Such a project can only be implemented with a sponsor, with the sound financing setup, because this has to cover the time of construction as well as the time of operation. Because the key point is that we want to achieve customer acceptance. This is fundamentally important to achieve all the goals we have with such a system. And the key point is the much lower energy consumption with higher speed, and of course, shorter travel time. So these three key aspects are basic ingredients to make the business model and the business case work. So this is at the end of the whole process, but we come back to the propulsion I was very happy to see the person who was before me, all the details which are being taken into account, the simulations, etc., to make this happen. So we have quite a process to go. I hope it will not be as long anymore as from 1993 to 2020, till we are able to get into a working and operating Hyperloop system. But there is still some way to go. And I'm very happy that you are interested in this topic because this is key. So you will take it with you in your professional career, and hopefully you will have the chance to implement it. I would be very happy to do that with my team, with any other interested people to achieve this goal. And this is one of my personal goals, to really do this in the next few years. And this is why we work together with Hyperloop technologies, transportation technologies, and other companies to achieve it. I wanted to show you a short video from HTT, but I will put it into the final version of the presentation because I'm here a little bit remote. Yeah, this is just in short what I wanted to talk to you. And I'm happy to take on some questions from the audience.
Thank you very much, Michele, for the presentation. I think you can, yes. Okay, so we'd like to go over to the questions. Somebody would like to know, what does certification mean? A lot of law involved.
Yes, not only laws, but also norms. Yeah, norms, for example, about fire safety. What happens in a capsule, or how do the materials behave in case high temperature is being encountered, or somebody tries to start a fire in a capsule. And this is a key aspect. So just to give you an idea, the materials don't have to get on fire, don't have to produce too much smoke, stuff like this. Other things are, for example, like ride safety. How is the reliability and safety of this thing, and what are the safety cases to be taken into account? Just to give you one idea, a key aspect is how, in case a capsule is stuck or stops in between somewhere in the tube, how will the passengers be evacuated? How do we open the doors? How do we bring the pressure to a level that people can come out? And how will they get to the next point of escape? Just two key points. Yeah, it sounds a little bit stupid and not very interesting, but it is very, very important. And as engineers, we have to have the answers to this, and we have to design the systems in such a way that we can demonstrate to a third party that this really works. See it as a certification process of an airplane. Maybe you have followed the Boeing 737 MAX, where during the certification something went wrong and then the accident happened. And now this has to be, or had to be rectified. And yeah, think about that, and then you know how complicated this can be.
Yes. Okay, then the next question. What does Typ Süd do exactly? Were you involved in the process? With which topics, etc.?
I didn't get the first part of the question.
The question is, what does Typ Süd do exactly?
Typ Süd is a certification body. They have specialists who know these norms and regulations very well, and they take a design apart and ask all these stupid questions to the engineers, which then leads to produce a lot of documents and explain what happens if the current goes away and how will the levitation change into a friction and the capsule stop and what will it do to the passengers inside. They ask stupid questions like this. I hope I was able to answer the question. So these are people, yes, please.
No, go ahead.
These are people, and they are very good engineers. They are from very different fields, and they listen very well what you say. They read your documents very well, and they ask all the questions.